Hi everyone, welcome back to Stat and Research 2. This week we're going to be focused on factorial designs, which is pretty cool. I really like them. But before getting into the lessons for this week, let's talk about some class assignments and announcements. First, your homework on factorial designs is due Saturday, like normal. I will be posting some more practice problems, practice midterm to help us prepare for our midterm, which is March 8th through the 12th. Again, you'll have a whole week, but once you start the exam, you'll have a specific amount of time. Also, to help us prepare for the exam, we'll have a live review session on Thursday, March 4th. Still trying to figure out a time. If you have any preferences on times for Thursday, March 4th, post it on Slack so I can start getting an idea of what times you guys might like. The practice problems will be extra credit and will be due by Wednesday, March 3rd by midnight so that I can post the solutions so that we can have a conversation on Thursday. I believe that is all of our class announcements. So recap, homework Saturday, practice problems will be posted soon where they'll be due March 3rd by midnight, review session March 4th, midterm the week of March 8th through the 12th. With that, let's get started talking about factorial designs. So again, this week we'll be covering factorial designs. Specifically in this lesson, we're going to be introducing factorial designs by talking about the aspects of design, treatment designs, error control designs, and then using a pesticide example to really illustrate where our factorial design is different than the other designs we've talked about thus far. Then I'm going to be going into the factorial model in ANOVA for a two-way and three-way factorial design. So let's get started. With the aspects of DOE, we've talked about this before, but our main objective is to understand the effect of treatments on the response. How we can do that is by using a treatment design, which is the protocol for how we define and apply treatments. We also have subsampling designs, which we'll talk more about next week. And subsampling is the protocol for measuring responses of the observational units. And then we have error control designs, which is the protocol to identify and account for systematic variability beyond that due to treatment differences. So what we typically do is we come up with a treatment design or a subsampling design, which is kind of our foundation of our design. And then we incorporate the error control designs. So for instance, if we are looking at our error control designs, we have our experimental error, which is decomposed into our systematic variability and our unexplained variability. And our goal with error control designs is to come up with a design where we can explain systematically as much variability as possible. And if we think about it in terms of maybe our CRD, we only had one source of systematic variability, which was just our treatment. And then we extended our design to a randomized complete block design where we had our treatment and our block. And then we went to the GRCBD where we had three sources of systematic variability, which was the treatment, the block, and the block treatment interaction. Now recall, the only reason we could estimate the block treatment interaction was because we have replicates. In the Latin square design, which we just talked about recently, there's also three sources of systematic variability, which is the treatment and then our two blocks represented in the rows and the columns. Now, our treatment design, we haven't really been too specific about it, but our treatment design is going to be the number of treatment factors, then the number of levels for each of those treatment factors, and then the next question is which treatment level combinations do we include? So thus far, all of our designs that we've talked about have only had one treatment factor. It might have been a combined treatment factor like our bologna example way back in lesson 2 or 3, where we talked about the mixtures. That example will come back up, don't worry. So we only had one treatment factor. factorial designs, we're going to start having 2, 3, and more treatment factors. So this is going to start becoming a question. The other question is how or which levels. Sometimes in your experiment, certain levels, if you have 2 or 3 treatment combinations, certain levels aren't allowed because of maybe if you do a certain combination, they'll blow up or whatnot. I'm thinking more engineering. You can't have certain levels mix. For our class, we're going to only be focused on a full factorial treatment design, which means that all the treatment level combinations we'll be looking at all the treatment combinations. There are other designs called fractional factorial treatment designs, which would just be a subset of all of the treatments. Okay, I will briefly talk about this at the end of lesson 7C. But for our class, when I say factorial treatment designs, I will always be referring to full factorial treatment designs, unless I otherwise say so. The reason I'm making this note is because in some classes you learn about both, and fractional design might not always mean full. In our class, it will. So let's talk about fractional treatment designs. We have a 2-way, which has 2 treatment factors, and then we have a 3-way fractional design, which is 3 treatments. Now, we could expand the factorial treatment designs to have 4, 5, 6 treatments, but those designs start to get really big in terms of the number of treatment combinations to look at. But once we understand 2- and 3-way factorial designs, we can apply and extend the idea to higher factorial designs, which we'll see today or in this lesson when I convert from a 2-way factorial treatment design to 3-way factorial treatment design. Once we have our number of treatments and our levels, i.e. our treatment design, we can combine it with any error control design, CRD, RCBD, GRCBD, BIBD, Latin square, etc. Hopefully you guys are getting the idea here. But for our class, we're only going to be focused on a 2-way, 3-way design combined with a completely randomized design. So our randomization is the treatment combinations randomly assigned to all the experimental units. So let's get a data set in here so we can maybe hopefully understand this a little bit better. So our pesticide example, which will be one of our examples that follows us through this lesson, is where an experiment was conducted to determine the effect of 4 pesticides on fruit yield from 3 varieties of citrus trees. 8 trees from each variety were randomly selected. The 4 pesticides were randomly assigned to the 24 trees, with each pesticide applied to 2 trees of each variety. To be a little bit more precise, it should be every pesticide variety combination was randomly assigned to the 24 plant sites in the garden. So in this example, our experimental unit is the 24 planting sites because we are randomly applying the pesticide variety combination to the sites. Additionally, we have one factor pesticides and the other factor variety, where both of these are treatments. And then we have our response right here for our cross of variety pesticide. These numbers in the shaded are the randomization, or how we randomized across all these trees. This is called the cell of our design. Here's one, and then here's another one. And if we average these numbers, we would get the cell mean, which is similar to what we would talked about in the GRCBD. Now note that we don't have a blocking factor here. And the reason we know that is because we didn't randomly apply one of these factors within the other factor. Okay, an example, if this was, repeat that again, if this was an RCBD, where let's say variety was our block, then we would have randomly applied the pesticide, our treatment, within here. So we would have had maybe 1, 2, 3, 4, 5, 6, 7, 8. So we would have had our we'd have randomized 1 through 8 here, randomized 1 through 8 here, and randomized 1 through 8 here. if we assume that this was a randomized complete block design where variety was the block. We can see that that's not how we randomize because we have our randomization 1, 2, 3, 4. It's all over the 24 plants. So so far we just kind of talked about factorial treatment designs, how we would randomize. And again, in our class, we'll be talking about full factorial designs with the error controlled design being in RCD. With that, let's now cover the statistical model, the parameter estimation, and the ANOVA, similar to what we've done with the other several designs we've talked about. We're going to start with a two-way, and then we'll build to a three-way factorial treatment design. So let's discuss some terminology. Now, with a two-way factorial treatment design, sometimes as a note, I might denote it as FTD in homeworks or whatnot. I don't believe I did it in the notes, but this would be a small abbreviation for factorial treatment designs. So we have two treatment factors, and rather than combining them into one factor, we're going to keep them separate and look at their treatment combinations. But we're going to call them factor A and factor B, where factor A is going to have lowercase a level, and factor B will have lowercase b number of levels. Our total number of treatment combinations is going to be T, and that's going to be A times B. Our number of replicates per treatment combination is going to be little n, and our total number of experimental units is going to be n times AB, or n times T. So if we go back up to this pesticide example, we will say that pesticide was factor A, and we can see that we had 4 levels, and so little a would be 4. Our variety would be factor B, and we had 3 levels, so little b would be 3. Our total number of treatment combinations is 12 because we have 4 times 3, and we can also see we have 12 cell blocks. We have 2 replications per treatment combination, and so our total number of citrus trees is 24. Again, this is all going to relate back to our completely randomized design that we've talked about before, but rather than just having one treatment factor, we have 2 treatment factors. Our statistical model for a two-way, the statistical model for a two-way factorial design is going to relate similarly to a RCBD. But again, here we're going to have 2 factors for our treatments rather than a treatment block. It's going to be, we have our main effect for our treatment, 1, and our second treatment, B. We then have an interaction term here, which allows us to look at the effect of one factor as the other factor changes. A lot of times this could be part of your research question that you're interested in. But again, the big difference between this statistical model, which looks similar to a GRCBD, is that our beta J is no longer a blocking factor, it's a treatment factor. For some statistical terminology, we now call this the main effect. Our alpha I is the main effect. Our beta J is also the main effect. And then our alpha beta is the interaction effect between treatments. We still have our random error assumption, normal, 0, and sigma squared. So we'll talk about the protocol and how we test in the next lesson. Right now, it's just to understand what is going on. So let's just recap what we've talked about between the GRCD and the two-way factorial. We have the same model, but in the GRCBD, this beta J here is a block effect that we're not interested in testing. But in the two-way factorial, this beta J is a treatment that we do want to test. Also, how we randomize our data is in the GRCBD, we randomize within block. And the two-way factorial design, we're going to randomize over all the EUs. Again, we're under our assumption CRD. Okay. Here we now have our summary statistics, similar to our last couple classes. I always provide you this, where our I is going to go from 1 to A. Our J is going to go from 1 to B. And our K is going to go from 1 to N. So subscript I is really representing the levels of treatment A, J is treatment B, K is the replicates. All right, so now that we've seen the two-way factorial treatment design, let's look at how we would do a three-way factorial treatment design. So we would have factor A, B, and C. These would be our treatments, each of them having their lower case level. Our total number of treatment combinations is still represented by T, but now we have A, B, and C. Multiplying those together, N is still representing our number of replicates, and our total number of EUs is little n times T, or little n times ABC. Our example that we're going to be using for our three-way factorial treatment design is our baloney example from lesson 3, I think. Don't quote me on that one. I don't really remember. But we've seen this baloney example before, right here. But before, when we were looking at it, we only looked at the mixture as our treatment. What we're going to do now is we're going to look at it as if it does have, but we're going to look at it through the 3 treatment factors, which is blend, which has 2 levels, the cognac flour, which also has 2 levels, and the SPI, which has 3 levels. So our total number of treatment combinations is going to be 12, because it would be 2 times 2 times 3. Our number of replicates is 3, because we have 1, 2, 3. And so our total number of samples, or EUs, is 36. You might be asking, we've done this problem before with just mixture as the treatment. Why would we might want to break it up into a three-way factorial design? The reason we would want to is because also the interesting thing about two-way and three-way factorial treatment designs is that we can look at the interaction and possibly get more information about the individual treatment levels. So before, we were really almost hiding this, and we were just saying mixture 1 through 12. But now we can start to get into more detail about certain individual treatment factors and all that. We have our summary statistics here. I'm going to do summary statistics, and then we'll talk about our model, where we are going to add a 4th subscript. So in this case, I is going to go from 1 to A, J is going to go from 1 to B, K is now going to go from 1 to C, and L is going to go from 1 to N. So notice the difference between our summary statistics from a two-way to a three-way. So we're adding another subscript to account for our 3rd factor here. And now our L is just going to have our replicates. Here's the summary statistics that if you guys want to look at them. And our statistical model is down here. We have our grand mean. We have our main effects here, alpha, beta, and gamma. We now have our two-way, can't make a box, two-way interactions, and we have a three-way interaction. Boom. And we still have our random error. Now, if we go to our parameter estimates for two-way and a three-way factorial design, we have our overall mean, which is averaging over all of the data. We have our treatment effect for A, our treatment effect for B, and our interaction. For three-way factorial, similar idea. Again, you guys won't have to memorize these, but it's always good to understand and have the formulas just in case something doesn't make sense. We then have our cell means and our residuals. The cell mean is the average of everything that receives the exact same treatment. Since we have, if we go back to our pesticide example, here we said that this was our cell, and so our cell mean would be the average of these two. Here's another cell, and so our cell mean for variety 3, pesticide 1 would be 67. It's the average of these two. And so the whole idea is that those two observations should be the same, and so any difference within the cell should just be background noise. Because we have replication, similar to the RCBD, we're able to estimate the interactions, so the estimated cell mean is just the average of the observations within the cell. And again, average within these cells. The residual is the observed value, so what we observe, minus what we expect to see, or our estimated cell means. We will talk a lot more about this in regression, which is after our midterm. And if you took a stat 5616, or you're in stat 5616, stat 5615, or any other intro stat classes, you've talked about simple linear regression and residuals. Cool. With that, we're now going to start talking about our partial total sums of squares, and we're going to start with our RCD. So again, the whole idea was that we have a treatment design now, which we have 2 or 3 treatment factors, and we're going to use the error-controlled design of a completely randomized design. And how our total sums of squares was broken up was through our sums of squares of treatments and our SSE, sums of squares of error, okay? And we had our sums of square total summing over just our treatments. But in this case, we now can break this treatment so that we have representation of both of our factors. This is going to be the sums of squares under the CRD with two-way factorial treatment design. So if we think about it, if we think about our bologna example, we originally were just testing mixture. So that would just be 1 to 12. But now, because we have 2 or 3 factors, we can break it up so that we're now summing over A and B. And so our total sums of squares now has A through B. So our total sums of treatment is going to have A and B. And same thing with our SSE. So our total sums of squares represents, so this here is going to represent the total treatment effect of A and B. Sometimes it's written as tab. I will probably keep it as SST. But we can decompose our sums of squares for our treatment into the sums of squares for effect A. You can't see what I'm drawing. Sometimes it's written as tab. Tab can be decomposed, or SST can be decomposed as the effect of A, the effect of B, and their interaction. And so how we do that is through these sums of squares. You guys don't have to memorize it, but sometimes it helps. And then we get to our factorial for our ANOVA, which is here. So we have our interaction, we have our main effect B, and our main effect A. Notice that we have F statistics now for our B. And the reason why is because this B is a treatment and not a block. And we're interested in testing this. Remember, we introduced blocks to help block out extra sources of variability. It's not something we're interested in testing. Now, this is a treatment, so we're interested in testing if it has an effect or not. A foreshadow to protocol is you're going to test your interaction first to see if you can then move to look at your main effects individually. How we test, your null is going to say the effect is equal to 0 versus the effect not equal to 0. The reason this effect is going to relate back to whether you're looking at the interaction or one of the main effects. You're going to look at the MSE, or the MS of the effect over the MSE with the respective degrees of freedom. Okay, i.e., you're going to be looking at these F stats. Okay, now if we move to a three-way factorial design under a CRD, our total sums of squares, again, we're just extending this part because we have more factors rather than just summing over treatments. Your sums of squares are here. Your sums of squares treatment can be decomposed into the effects of factor A, B, C, as well as the interaction of AB, the interaction of AC, interaction of BC, and the interaction of all three. Here are your sums of squares if you want to look at them. And you're left then with our ANOVA table, where we have our three-way interaction, two ways, and then our main effects. Again, we have our F statistics because we're interested in testing these and they're not blocks. Our protocol for testing will, which we're going to talk about in our next lecture, will focus on looking at the three-way interaction to see if we can then move to our two-way interactions to then see if we can move to our main effects. More about that in our next lesson.